Sequence alignment in linear space via divide and conquer. In the previous section, we showed how to compute the optimal alignment between two streams x and y of lengths m and n, respectively, building up the two-dimensional m by n array of optimal solutions to subproblems, OPT dot dot, turned out to be equivalent to constructing a graph gxy with m and nodes laid out in a grid and looking for the cheapest path between opposite corners. In either of these ways of formulating the dynamic programming algorithm, the running time is big O of mn because it takes a constant time to determine the value in each of the mn cells of the array OPT, and the space requirement is big O of mn as well, since it was dominated by the cost of storing the array or the graph gxy. The question we ask in this section is, should we be happy with big O of mn as a space bound if our application is to compare English words or even English sentences? It is quite reasonable. In the biological applications of a sentence of sequence alignment, however, one often compares very long streams against one another, and in these cases, the theta of mn space requirement can potentially be a more severe problem than the theta of mn time requirement. Suppose, for example, that we are comparing two streams of 100,000 symbols each. Depending on the underlying processor, the prospect of performing roughly 10 billion primitive operations might be less cause for worry than the prospect of working with a single 10 gigabyte array. Fortunately, this is not the end of the story. In this section, we described a very clever enhancement of the sequence alignment algorithm that makes it work in big O of mn time using only big O of m plus n space. In other words, we can bring the space requirement down to linear while blowing up the running time by at most an additional constant factor. For ease of presentation, we'll describe the various steps in terms of paths in the graph gxy with the natural equivalence back to the sequence alignment problem. Thus, when we seek the pairs in the optimal alignment, we can equivalently ask for the addresses in the shortest corner-to-corner path in gxy. The algorithm itself will be a nice application of divide and conquer ideas. The crux of the technique is the observation that if we divided the problem into several recursive calls, then the space needed for the computation can be reused for one call to the next. The way in which this idea is used, however, is fairly subtle. Designing the algorithm. We first show that if we only care about the value of the optimal alignment and not the alignment itself, it is easy to get away with linear space. The crucial observation is that to fill in an array of the array A, an entry of an array A, the recurrence in 6.16 only needs information from the current column of A and the previous column of A. Thus, we will collapse the array A to an n by n array B as the algorithm iterates through values of j. Entries of the form B of I0 will hold the previous column's value A of I j minus 1, while entries of the forms B of I1 will hold the current column's value A of ij. Space efficient alignment algorithm is described as follows. With the input x and y, we have a two-dimensional array B with rows from 0 to m and the columns from 0 to 1. Initialize B of I0 equals to I delta for each I, just as in column 0 of A. Now for j equals to 1 to 3 until n, B of 0, 1 is equals to j delta, since this corresponds to the entry A of 0j. For I, now there's an inner loop for the outer loop of j from 1 to n. This inner loop going through from I starting from 1 to 3 until m with the value B of I1 equals to the minima taken among alpha xi yj plus B of I minus 1 0 and the delta plus b of I minus 1, 1, and the delta plus b of I, 0, and 4. Now, after we break out from the inner loop, we move column 1 of b to column 0, and to make room for next iteration, updated the b of I0 equals to b of I1 for each I. So that's it. It is easy to verify that when this algorithm completes, the array entry b of I1 holds the value of OBT of IN for I equals to 0, 1, 2, 3 until m. Moreover, it uses big O of mn time and big O of m space. The problem is, where is the alignment itself? We haven't left enough information around to be able to run a procedure like find alignment, since a b at the end of the algorithm only contains the last two columns of the original dynamic programming array A. If we were to try tracing back to get the path, we'd run out of information after just these two columns. We could imagine getting around this difficulty by trying to predict what the alignment is going to be in the process of running our space-efficient procedure. In particular, as we compute the values in the jth column of the now implicit array A, we could try hypothesizing that a certain array has a very small value, and hence that the alignment that passes through this entry is a promising candidate to be the optimal one. But this promising alignment might run into big problems later on, and a different alignment that currently looks much less attractive could turn out to be the optimal one. There is, in fact, a solution to this problem. We will be able to recover the alignment itself using big O of m plus n space, but it requires a genuinely new idea. The insight is based on employing the divide and conquer technique that we've seen earlier in the book. We begin with a simple alternative way to implement the basic dynamic programming solution. A backward formulation of the dynamic program. Recall that we use f of ij to denote the length of the shortest path from 0, 0 to ij in a graph gxy, as we showed in the initial sequence alignment algorithm. F of ij has the same value as OPT of ij. Now let's define g of ij to be the length of the shortest path from ij to mn in gxy. The function g provides an equally natural dynamic programming approach to sequence alignment, except that we build it up in a reverse. We start with g of mn equals to 0, and the answer we want is g of 0, 0. By strict analogy with the 6.16, we have the following recurrence for g. 6.18. For I less than m and j less than n, we have a g of ij equals to the minima chosen among the following values. Either we choose alpha x I plus 1 y j plus 1 plus g of I plus 1 j plus 1, or we choose delta plus g of I j plus 1, or we choose delta plus g of I plus 1 and j. This is just the recurrence one obtains by taking the graph gxy, rotating it so that the node mn is in the lower left corner, and use the previous approach. Unlike this picture, we can also work out the full dynamic programming algorithm to build up the values of g backward starting from mn. Similarly, there is a space-efficient version of this backward dynamic programming algorithm, analogous to space-efficient alignment, which computes the value of the optimal aligning using only big O of m plus n space. We will refer to this backward version naturally enough as backward space-efficient alignment, combining the forward and backward formulations. So now we have symmetric algorithms which build up the values of the functions f and g. The idea will be to use these two algorithms in concert to find the optimal alignment. First, here are two basic facts summarizing some relationships between the functions f and g. 6.19. The length of the shortest corner-to-corner path in Gxy that passes through ij is f of ij plus g of ij. Proof. Let Lij denote the length of the shortest corner-to-corner path in Gxy that passes through ij. Clearly, any such path must go from 0, 0 to ij, and then from ij to mn. Thus, its length is at least f of ij plus g of ij, and so we have that Lij is greater than or equals to f of ij plus g of ij. On the other hand, consider the corner-to-corner path that consists of a minimal length path from 0, 0 to ij, followed by a minimal length path from ij to mn. This path has length f of ij plus g of ij, and so we have Lij which is less than or equals to f of ij plus g of ij. It follows that Lij is equals to f of ij plus g of ij. 6.20. For let k be any number in the set between 0, 1, 2, 3 until n, and let q be an index that minimizes the quantity f of qk plus g of qk. Then there is a corner-to-corner path of minimal length that passes through the node qk. Proof. Let L star denote the length of the shortest corner-to-corner path in Gxy. Now fix a value of k which is in the set 0, 1, 2, 3 until n. The shortest corner-to-corner path must use some node in the kth column of Gxy. Let's suppose it is node pk, and thus by 6.19, L star is equals to f of pk plus g of pk, which is greater than or equals to the minima of f of qk plus g of qk, where the minima is taken among all the possible q. Now consider the index q that achieves the minima in the right-hand side of this expression. We have L star which is greater than or equals to f of qk plus g of qk. By 6.19 again, the shortest corner-to-corner path using the node qk has length f of qk plus g of qk, and since L star is the minimal length of any corner-to-corner path, we have L star which is less than or equals to f of qk plus g of qk. It follows that L star is equals to f of qk plus g of qk. Thus, the shortest corner-to-corner path using node qk has length L star, and this proves 6.20. Using 6.20 and our space-efficient algorithms to compute the value of the optimal alignment, we will proceed as follows. We divided Gxy along its corner, its center column, and compute the value of f of I m divided by 2 and g of I m divided by 2 for each value of I using our two space-efficient algorithms. We can then determine the minimal value of f of I m minus 2 plus g of I m minus 2 and conclude via 6.20 that there is a shortest corner-to-corner path passing through the node I n over 2. Given this, we can search for the shortest path recursively in the portion of Gxy between 0, 0 and I m over 2 in the portion between I n over 2 and m n. The crucial point is that we apply these recursive calls sequentially and reuse the working space from one call to the next. Thus, since we only work on one recursive call at a time, the total space usage is big O of m plus n. The key question we have to resolve is whether the running time of this algorithm remains big O of m n. In running the algorithm, we maintain a globally accessible list p which will hold nodes on the shortest corner-to-corner path as they are discovered. Initially, p is empty. P need only have m plus n entries, since no corner-to-corner path can use more than this many addresses. We also use the following notation. X with the index from I to j, for 1 is less than equals to I, less than equals to j, less than equals to m, denotes the substring of x consisting of xi, xi plus 1, xi plus 2, and so on until xj, and we define y with the index from I to j. Analogously, we will assume for simplicity that n is a power of 2. And this assumption makes the discussion much cleaner, although it can be easily avoided. So the following is the algorithm. Divide and conquer alignment of x, y. Let m be the number of symbols in x. Let n be the number of symbols in y. If m is less than or equals to 2 or n is less than or equals to 2, then compute the optimal alignment using alignment of x, y. Call space efficient alignment x and y with index from 1 to n over 2. Call backward space efficient alignment of x and y with index from n over 2 plus 1 until n. Let q be the index minimizing f of q n over 2 plus g of q n over 2. Add q n over 2 to global lost p. Then we use the recursive call. Okay, divide and conquer call itself with a smaller range of parameters. That is x of index between 1 to q and y of index between 1 to n over 2. Then we call another recursive call for divide and conquer alignment with x with range between index q plus 1 until n, and y with index range between n over 2 plus 1 until n. Finally, we return p. As an example of the first level of a recursion, consider figure 6.19. If the minimizing index q turns out to be 1, we get the two subproblems pictured. Analyzing the algorithm. The previous arguments already established that the algorithm returns the correct answer and that it uses big O of m plus n space. Thus, we need only verify the following fact. The running time of a divide and conquer alignment on strings of length m and n is big O of mn. Proof. Let T of mn denote the maximum running time of the algorithm on strings of length m and n. The algorithm performs big O of mn work to build up the arrays b and b prime. It then runs recursively on strings of size q and n over 2. It then runs recursively on strings of size q and n over 2 and n over 2. Thus, for some strings of size m and some choice of index q, thus for some constant c and some choice of index q, we have cmn which is less than or equals to cmn and plus t of n over 2 n over 2 plus t of m minus q and n over 2, which is less than or equals to. Another constraint is t of m2 is less than or equals to cmn. The third one plus is t of 2n is less than divided by 2 plus k times this recurrence minus q times is more complex than the ones we've seen in our earlier applications of divide and conquer in chapter 5. Plus k first of all, the running time is a function of two variables, m and n, equals to rather than just c 1. Plus k also, over the division into subproblems is not necessarily an even split. But instead, this recurrence is more complex than the ones with the earlier work done in our earlier applications. So how should we go about solving such a recurrence? One way is to try guessing the form by considering a special case of the recurrence and then using partial substitution to fill out the details of this guess. Especially suppose that we were in a case in which m is equals to n and in which the split point q were exactly in the middle. In this admittedly restrictive special case, we could write the function t dot in terms of the single variable n, set q equals to n over 2, since we are assuming a perfect bisection, and have t of n, which is less than or equals to 2 times t of n over 2 plus c times n squared. This is a useful expression, since it's something that we solved in our earlier discussion of recurrences at the outset of chapter 5. Specifically, this recurrence implies T of n is equals to big O of n squared. So, when m is equals to n and we get an even split, the running time grows like the square of n. Motivated by this, we move back to the fully general recurrence for the problem at hand and guess that T of mn grows like the product of m and n. Specifically, we'll guess that T of mn, which is less than or equals to kmn, for some constant k, and see if we can prove this by induction. To start with the base cases m, which is less than or equals to 2, and n, which is less than or equals to 2, we see that these hold as long as k, which is greater than or equals to c over 2. Now, assuming T of m prime, which is less than or equals to k times m prime, holds for pairs m prime. With a smaller product, we have T of mn, which is less than or equals to cmn, plus T of q n over 2, plus T of m minus q n over 2, which is less than or equals to cmn, plus kqn over 2, plus k times m minus q times n over 2, which is equals to cmn plus kqn over 2, plus kmn over 2 minus kqn over 2, which is equals to c plus k over 2, then times m, then times n. Thus, the inductive step will work if we choose k equals to 2c, and thus completes the proof.